Machine learning is often treated as magic, but underneath the hood, it is driven by accessible math and data. In this video, we are going to break down how machines learn by following a three-part journey: basic data analysis, contextual chatbots, and dynamic probability. We start at level 1. Basic data analysis is strictly the search for historical patterns within a static environment. This table shows exactly what that looks like. We have organized raw facts, historical dates in one column, and recorded temperatures in the other. This tabular format serves as the foundation for all machine learning models because it translates human observations into a machine-readable format. But simply organizing past data is not learning. To actually learn, a system has to use this historical foundation to anticipate and predict the unknown. That brings us to the first major mathematical hurdle in AI: transitioning from analyzing what has already happened to actively predicting what will happen next. This scatter plot maps a gardener's fertilizer applied against the resulting plant growth, the basis of linear regression. By establishing a mathematical trend, the system follows that line into blank coordinate space, calculating a prediction for a fertilizer amount that hasn't been tested. Calculating and extending this trend line is the exact mechanism that shifts a computer from a static historical database into an active predictive engine. While linear trends work for numerical values, human language requires a different approach. A chatbot relying on rigid if-then rules cannot sustain a natural conversation because it lacks context. This diagram shows the solution. On the left, a logic tree breaks down the moment a user deviates from a pre-programmed path. On the right, we have a memory store module. This architecture, known as session state, acts as a context window that remembers previous interactions and actively feeds them back into the core NLP model. By looping this conversational context, the system processes human language as a continuous flow rather than a series of isolated commands. Let's apply this to a real-time scenario. Imagine a video game boss programmed to expect a left side attack 30% of the time. Now, the player suddenly equips a left-handed shield. Pause here and think about how the boss's code should mathematically adjust to this new behavior. To handle this, the game dynamically updates its internal logic using Bayes' theorem. The unbroken square represents 100% of possible player attacks, with this slice representing the initial 30% probability of a left attack. When receiving new evidence, the left-handed shield, the system mathematically eliminates unobserved possibilities. The remaining area resizes, forming the AI's new baseline probability. This continuous mathematical loop of shrinking possibilities based on new evidence is the engine that allows AI to adapt to its environment in real time. All three of these distinct concepts converge in real-world applications, like the architecture of a streaming platform's movie recommender system. This conceptual interface shows how the layers work together simultaneously. Linear regression predicts the user's base ratings for new movies. Session state tracks the context of their recent genre searches, and Bayes' theorem recalculates their profile probabilities instantly the moment they click the thumbs up button. These three mathematical pillars, linear predictions, contextual memory, and probability updates, provide the foundation for building more layered models. This chart shows how these same principles scale, moving from single decision trees to the multi-layer networks used for deep learning. Understanding these mathematical principles translates the black box of artificial intelligence into a comprehensible, structured tool. If you want to continue mastering the mechanics of machine learning, like this video and subscribe for more deep dives.